Go. This is Michael. I'm joined by Neil. Hey, Neil.
Hey, Michael. How's it going?
Pretty good. We're here for part 2 of visual analytics in time and space, or space and time, I guess, on this slide. We ready to roll?
We are. This is a continuation of our last presentation, right?
Yeah, exactly. So last time we got, for the most part, into the time, through most of the time piece. We're going to pick that up with a recap today, and then do the space piece and wrap it up with the space-time component. So let me kick it off with just a recap of some of the visual analytics principles that we got into last time: perception, estimation, inference, and insights. That's the sequence. And just to recap, that folks understand how we perceive patterns as humans. And the goal of the author is to layer into the way that we perceive patterns as humans. And the thing is that accuracy and speed are both important. So you want to be able to do your visual analytics in a way that people can detect, recognize the geometry and codings of the values, to get more detailed about it, to allow people to assemble, groupings of graphic symbols and elements to construct the patterns, and then allow people to estimate from the visual display to get an assessment of relative magnitudes of one variable versus another, for example. Now, this all happens in like microseconds. The human brain can process entire images that the eye sees for as little as 13 milliseconds. So when you come to a graphic, you can really communicate a lot of information right away. The figure down the bottom there emphasizes that you can see a circle immediately on the left, and to read that description, a curved line with every point equal distance from the center, that takes a long time to process, but your brain and eye can just immediately see that symbol. So you want to kind of put out symbols in a way that you can get comparisons, you can get insights, all the way from estimation to inference to insight. And so we spoke last time about that. And here's an example we used in that narrative around electric power usage from Friday morning on the left to Sunday afternoon on the right. And this is data that you can see that across the top left, this is a business where you've got power consumption pretty consistently, each of the 3 days, Friday, Saturday, Sunday. Well, the next one is in the evening. You're getting consumption in the evening. So this is restaurants and nightclubs. The bottom one is just consistent usage across the 24 hours of each of the 3 days. This is kind of a single family home. The top right looks like broken meters. Downtown businesses where you've got a lot of activity on Friday and then less on Saturday and then less on Sunday. And then condos with that, spike on Saturdays. People are at home, not at work. So, these patterns, you can see them very quickly with your eye, and you can kind of understand what they are. And putting a smooth curve through that really helps. And we'll show you some tricks about how to bring out insights from the data like that. So let's step through estimation, inference, insights real quick. Estimation, you want humans to compare things on lines, points, colors, shapes on graphs. And bottom line is humans are not great at estimating differences. They're okay at looking at estimating differences on lines, but not when the lines get too steep. Humans don't naturally order color hues, and so only a limited number of hues can be discriminated. So you don't want to use too many colors on a visual. Red is an emotional color, maybe perceived as larger and have other emotional connotations. Shading, larger regions appear darker. So you want to take all those things into account. And then with respect to lines, Weber's law, the probability of a human detecting a difference in 2 lines is related to the ratio of the line lengths. Grid lines can help. Sorting by order of categorical values can be helpful. And then scatter plots, if you're using scatter plots with 2 variables on there, you want to make sure the aspect ratio, the average of the slopes is 45 degrees. This is Bill Cleveland's principle, banking to 45 degrees. If you kind of make the average 45 degrees, it makes it easier to distinguish the 2 slopes. So just to quickly go through these, the order of human perception abilities, position on a common scale is most accurate. You can see, actually, this is a screenshot from Stephen Pugh's book. Now you see it, and you can see how longer is greater, and you can see quite precise at determining the difference between those lines. 2D position, again, pretty precise about looking at the difference there. But once you get to, widths and sizes and intensities kind of below the line here, you can see that is that line there you can see is thicker, but you don't know by how much. This point here is bigger, but you don't really know by how much. This shading is lighter, but you don't really know by how much. So, area volume and color hue saturation are things that we don't compare. When it comes to making inference, we're not great at getting the quantity of difference between those two things. Whereas, position along a common scale and position along identical non-aligned scales, we are pretty good at getting inference off that. So that's estimation, that's inference, and then when it comes to color and the use of charts, length is much better than area. And so in this graph, we've got length along the bottom works very well, but area along the top does not work well for inference. And so you see these three charts across the top, Los Angeles, Seattle, and New York. You can't tell, in which of those cities you're selling more clothing or more furniture or more electronics, the different colors. Whereas if you put them, on a common scale, and you can make the comparison, draw the inference that Los Angeles sells less clothing and more toys. New York is the opposite, more clothing and less toys, and Seattle's kind of all over the map. So, the length piece human do very well above the line, but the area piece below the line here, we don't do very well. And then when it comes to, the banking to 45 degrees here, you can see that on the top graph, it's difficult to pull out the which of these three colors is the slope is different. But when the bottom right, when you've banked the slope to 45 degrees, so the average slope on the bottom graph is 45 degrees, you can very quickly see that the slope of the blue is quite different to the slope of the yellow. So that's a big principle of Bill Cleveland's, this idea of setting the average slope to 45 degrees allows you to better discriminate between, in this case, three lines from blue to red to yellow, whereas at the top one it's really difficult to tell that apart. And another principle here is around the idea of having a common scale. And this is data from our COVID work. And you can see here that we've set the cases to the common scale of 100 on the y-axis, 100 per 100,000. And the vaccination rate as a percentage, we're setting from 0 to 50%. So that allows us to go through and compare different countries with respect to their case rate on the left and their vaccination rate on the right. So I see the United States, I see the United Kingdom. I've got those in my mind about their case rate and vaccination rate as France. I can see the differences in my mind. I'm assimilating the differences between cases on the left and vaccination rate on the right by country as I click around the countries. Now, when India, has low cases and low vaccination rate, you can use the zoom slider to zoom that up to see, the shape of that. So you've got the consistency of the two axes for comparing the multiple countries. And then you've also got the ability to use the zoom slider to get more detail on a country, in this case, that has lower case counts than the others, and you can want to get into the detail of it. So that's another tip there on inference. Neil, I think I've jumped ahead here. Do you want to make any quick comments before you take us through a recap of how we use color?
Yeah, no, I think the way that you fix those scales really helps compare do comparisons of relative between the countries. If we didn't have fixed those scales, you would see this line jumping up and down, and that would have been a lot harder to compare on the cases per 100,000. So fixing scales can be really useful when you're doing comparison of data side by side. And I think on the previous slide, I like the way the 45-degree angle you can see on the bottom right image. It really helps you see those outliers in yellow. By banking to 45 degrees, we're seeing a better representation of all of those trend lines, and we're orienting our data so that we're orienting the chart so that our data, the general trend lines along 45 degrees, and those yellow points that are on the right of the chart we can see that those are outliers in the y-axis a lot better than the chart above that, where it looks like they're just outliers on the x-axis. So that ratio is really important.
Right. One of the comment I wanted to make was this fixing the scales is super important when it comes to time data and real-time data as well, so that you can see different points arriving onto the layout of the x and y axis, and you don't have to adjust your mind to moving axes. So I think that's an important principle to keep in mind for a data that's arriving in time, as well as with this particular data where you've got a time series.
Absolutely. Yeah, and if we move forward to the color side, so there's different ways we can use color to enhance visual perception now. This is something we've talked about in the past, but a quick recap is you have generally 4 different types of color schemes: binary, qualitative, diverging, sequential. In binaries, we're gonna have 2 different colors, like true or false, yes or no. It can be Democrat, Republican, it can be, left, right, whatever. So those are 2 different sides. Now, diverging, you're going to have 2 different extremes, but you're going to have a numerical. It's not going to be categorical. So you may have different gradients, different degrees of each of these extremes. So we'll show an example of that coming up. And then qualitative on the top right, there's no real ordering to it. It's just qualitative. It's categorical. And then sequential on the bottom right, that is numerical, but that is going from one minimum to a maximum point. It's going in one direction, and that goes in a sequence. If you can move forward, next slide, Michael. This is an example with honeybee colonies, and this is a colony yield, how much honey is being yielded. So the same data is being used in all 4 charts, and in the top chart, you're seeing, is this above average or is this below average? The green states are above average. So I've taken the yield and I've categorized that into a binary color scheme, just above or below average. Below that, we use diverging scheme. So how much above or below average? And you're seeing a different shade there of how much, how green or how gold each state is showing how much above or below average it is. And then on the right, bottom right, you see a sequential thing where it starts from the minimum yield, which is going to be the lighter states, and it goes to darker states, which is going to be Louisiana, North Dakota. You're seeing more honeybee yield. That's darker states. Now on the top right, we use a qualitative thing where we're not using any numerical values at all. And this is just qualitative, just to show different regions of the US. So there's 4 different themes there. Same chart, same type of chart, which is a map chart, same type of data, but 4 different representations of that. You move on to the next slide. Yeah. So in human perception and insights, Ben Schneiderman's visual analytics mantra, he talks about 3 levels of understanding: overview, filter, mark, and zoom to areas of interest, and then see details on demand. So if we watch this little video, what we're looking at is New York City demographics on the right. And as I play this video, you're seeing I'm able to filter by moving. We have a star there that's on the map, and we're filtering down to what's nearest to the star. Then we're able to mark areas of interest. So the mouse is going to go down and mark certain high income areas. And then we can hover over those points on the map and get the details. So details on demand pop up as a little tooltip. So this is this gives us speed and accuracy in terms of our interpretation. Many graphs have a lot of data in them. And so how do you zoom in on that data? How do you take the broad scope of data and actually find the insights? So this filter, mark, and zoom is a great way to actually use the interactivity of a visual analytics tool to find those insights in your data.
Yeah, and the details on demand in this case show up right there on the tooltip about that new store, average income, total population, stuff like that. Okay, so that's a quick recap of the principles of display, estimation, inference, insights, the 3 levels, Ben's mantra there: overview first, zoom and filter, and details on demand. Now, just a quick recap on time and time varying displays. Line chart is obviously the most common, and you'll see when you bring start a line chart in Spotfire, for example. This is created in Spotfire. The time axis is defaulted to time. The x-axis is defaulted to time. In this case, we're looking at life expectancy from different predictions, and you can see quickly, you can easily compare those. And this is a good display for continuous timelines, categorical variable comparisons, magnitude changes, historical trends, forecasts. So that's a real go-to chart. If you've got ranks versus continuous data, then the bump chart is pretty good. It shows comparing cryptocurrency market caps there on the left across time, and you can see the relative rank of different types of crypto here. So good for relative magnitudes when you just want to order things versus get continuous quantitative inference. This one is looking at a velocity chart where we fit a smooth curve to case counts along the top there, case count on the y-axis, COVID cases. On the bottom, we've off that smooth curve, we've estimated a first derivative. So you can quickly see what the growth rate is at any point in time, as well as the actual on the top, the case count. So case count, growth rate, trend analysis, the velocity chart is pretty useful. Candlestick chart, this is pretty specialized to financial services. So this is financial data with price movements on a particular time interval, mostly often a day, where the body of the box plot is the range of price between open and close. The whiskers are the high-low points of trading. The bar chart along the bottom of the x-axis is the volume traded. And then the color is used to indicate trending up, bullish, or down, bearish. So you can quickly get a view of this. When you've got a volatile market like we have right now, you can get a really quick understanding of different stocks and how they're comparing with the candlestick chart. With animations, this is where you want to put time, as the way things update in the canvas. And in this case, you've got cases on the y-axis versus, let's see, you've got vaccinations, on the y-axis and new cases on the x-axis. You've got the individual states here, and what's playing in the animation is the time sequence. So this is good for storytelling, observing relative change. It's not good if you want to make a report or track a lot of data points. But here we'll just run this real quick. And this is, you can see people vaccinated per 100 on the y-axis, new cases per 100,000 on the x-axis, the individual states there. The timepiece is coming through that date that's being displayed on the body of the graph. You see we're in May now, and you can see when we got to May, there's quite a big disparity between states that are highly vaccinated like Vermont and states that are lowly vaccinated like Mississippi. And you can see when the variant came in that the states along the bottom, the lowly vaccinated states, had a surge in cases. The x-axis position of those states moved quickly to the right. And now when the second variant came in, you can see that affected all the states, and all the states are moving to the right, regardless of their vaccination rate. Looks like the things are coming back pretty aggressively now. This is we're through a lot of this, but you can see how this, Hans Rosling made this chart popular with his Gapminder analysis and analysis of different countries with respect to their life expectancy rates and so on. We've used it for vaccination versus new cases with the time variable coming through on the canvas. Another great time analysis here is where we're looking at different wells across Texas, and we're understanding the state of the asset. You can see that there's a pressure in one column and motor amperage current in another column. In this case, if the pressure gets too high, you want the red color to come through. If the current gets too low, you want the red current to come through. So one high is bad, the other one low is bad. And you can see how we've used the on the spatial representation, the state of those wells changes color, and also on the right-hand side, the graphs of pressure on the top and motor on the bottom. You can see how they're colored. When it goes too low on current, its color is red. When it goes too high on pressure, color is red. And you're able to set alerts about where you want the color changes to occur. And we've made those alerts go through the table, through the map, and through the line chart. Okay, so
I thought we'd answer a couple questions that we've seen.
Oh yeah, sure. Let's
so Kate was asking how easy it might be to create a New York City demographics dashboard that we show with our filter mark and zoom. And it's pretty easy with Spotfire. The visualizations are all drag and drop. So you can just place them wherever you want on the visual canvas, and then it automatically brush links, automatically does the drill downs for you. You can then do further customizations like the colors and customize like what shows up in the tooltip, where you want to put the filter. If you remember, I moved the filter over on that visualization, but it's all pretty self-service and pretty easy to do. There was also another question about using how many colors to use, and Carolina was wondering how many colors to use for best practices in a visualization. And I think 5 or 6 colors is typically like the max that you can really start to perceive when you go around the color wheel and you divide that into 5 or 6 chunks. That's when you're going to be able to make a good be able to distinguish well between those different colors. Once you start going into more colors, they tend to run together. So you can do things like decreasing the saturation or the hue of each of those colors, and then highlighting the insights that you want to show on top of that. Or you can use something like a grayscale, using like gray colors to de-emphasize the data that is not part of the insights, and then using something like a stronger color to show the insights. So if I actually go back to, if you give me just a second here, I'll go back to that bump chart. So this bump chart, so this is as Carolina mentioned, there's a lot of colors here, and this can be overwhelming. What I maybe want to do is focus on what are some of the more volatile cryptocurrencies. So you're seeing a line over here. This is volatile for this cryptocurrency. I may want to start graying out some of the other cryptocurrencies, the other values, and then just focus on just 1 or 2 of these cryptocurrencies. So it depends on the insight that I want to show. Another thing I could do is just make this a bright red color, and then make the other colors a much lighter color, and that will help emphasize what I want to show. So those are a couple of examples of that.
Yeah, great question, great comment, Carolina.
Yeah.
So there's a challenge, Ravit. What's one challenge customers usually face when it comes to visual analytics? Wow, I think that's what the whole focus of this talk is trying to help customers with a variety of challenges. So I think let's keep going. Neil, do you want to get into we're up to the space section, right? Pretty much.
Yeah, definitely. Do you want to? I can just continue from my screen if you like.
Yeah, continue from your screen. Yeah.
Okay.
It looks like we've got one more time example here, and this is data on traffic patterns, and we've actually doing some analytics here, some advanced calculations. We're doing an object tracking analysis where we're putting bounding box around different cars and measuring their speed and real-time data feed. I think we've got a video of this, Neil, if you want to run it. So yeah, this is a final example on the time section here, where we're looking at traffic patterns from a video camera. We're putting a bounding box around them that even allows for occlusion of one object in front of the other. We're calculating speeds. We're displaying the cars driving. We're looking at the different types of cars and vehicles and their speed, and doing some summary stats on it with the video combined. So that's the last example, I think, on the time section. Neil, let's get into the space, which is the focus of today.
Yeah, the focus of today's talk was the space. So a lot of what we just showed was a recap of some of the topics we've talked about in the past, but now we're going to go into some new topics on space and how we use spatial principles for visual analytics. So some of the basic principles, the benefits of spatial data is that you have improved interpretability of size, shape, boundaries, density, proximity, and context. There's just so much context you get from a map chart or a spatial chart. You're able to see the road networks. You're able to see the water patterns, the water bodies that are around here. You're able to see the sizes of certain boundaries in certain regions. It's just so rich with what you can get with a spatial chart. It's one of my favorite charts to use. So what is a spatial chart comprised of? So typically it's going to be points, lines, or polygons. Those are your geometry data. These are the type of data that's used in shape files very often. And with points, lines, and polygons, you can construct any type of spatial visualization. So what's shown here is actually a floor plan of the San Francisco airport, and this is comprised all of lines and polygons with different parts of that map all kind of laid out and labeled. So what is a geographical map? Now, a geographical map or a map in itself is a visual representation of different objects, roadways, water bodies, what have you. And that's often shown in a geographical map. There are other types of maps, but let's talk about a few of them. The geographical map is probably the most commonly talked about map. And this has, there can be a topographic type of map, a climatic, economic map. Typically displays data relative to global latitudes and longitudes. So it's typically on the surface of the Earth. Now, the way that that's projected on the Earth is going to be dependent on your map projections. Now, your map projections can really distort your spatial data. That is how those points lie on the surface, right? So you can see in a Mercator projection that, you know, Australia is much smaller looking than it might look like in a where is it in the Robinson projection, where Robinson projection might look much larger. So what you want is a good projection that suits the needs of your data and suits the needs of what you're trying to communicate. And you might use different coordinate reference systems there as well. These are the actual datums on which how your points are represented on that surface. Michael, did you want to add any comments on the projections there?
Let me see, Neil. Sorry. No, yeah. I think you got it. You nailed it. Yeah.
Okay. Moving forward, so here's a choropleth map, and a choropleth is different from what we might see in a typical bubble map or a marker layer map where you have different points representing your data. In a choropleth, we're actually going to use the boundaries of certain areas to represent our data. So what you're seeing here is this prevents the overlap of bubble data. If you have different markers on top of each other, it can be hard to interpret your data. The choropleth actually shows your data like side by side within certain regions. So what we're seeing is unemployment during the COVID-19 pandemic, and this is unemployment in the United States by county. Over here, we're seeing growth rates of different COVID-19 trends on COVID-19 case counts, and this is by country. This can create distortions if you don't normalize your data correctly. You want to normalize your data by population often, or whatever denominator variable that you might have in the insights that you're trying to project. It can create distortions because you have some counties, for instance, that are much larger than other counties. And so it might look like that's a lot more area, but it's really just representing a larger county. So a way that you can get around that visual bias is a cartogram. Cartograms actually distort the shapes of those objects based off of the data that you're trying to represent. So this is COVID-19 cases in the United States, and you're seeing when cases were first starting, you see New York, you see Florida, Texas, California, the more populous states, they're kind of blowing up there. Whereas you see Wyoming over here, which is a much less populous state. It's a good size, but much less populous. That's actually kind of shrinking there. So a cartogram actually helps reduce the bias that you might see in geographic boundaries. So that's a useful form of that. We talked about the floor plan and building map. The floor plan and building map are ways. These are not necessarily geographical maps as they would lay on the surface of the Earth, but they may be pointed in different directions. They indicate resources and accessibility. They can be interactive with interactive polygons. So this is another type of map. And then next is actually a tree map. So a tree map is non-geographical in nature as well. And this is actually showing the volume of traffic in certain buildings on the Dartmouth campus. So we were looking at COVID-19 data and COVID-19 safety precautions on the Dartmouth campus, and we could see which rooms. What we're seeing here in the dark red are in the dark red is the most populated rooms. What you're seeing by the size is the size of the room. So this is a rather large room that's being well trafficked. This is a rather large room that's not being trafficked as much. And then we see some green rooms here, which are smaller rooms that aren't being visited as often. So the tree map is the feature location is not necessarily physical, and the proximity of these features are arranged by a hierarchy. So you have color and size to represent these different variables, and this is using 100% of the real estate available to you. So it's a very efficient use of the real estate. There's not a lot of white space in here.
Yeah, Neil, someone's asking, saying how awesome these examples are, and asking if they're a gallery of demos. So I just stuck up the demo gallery in the chat for people to look at some of these as we're going along.
Okay, great. Yeah, we have a bunch of demos in that demo gallery. Michael just put this up in the chat. Let me see if I can.
And I noticed, Jolene, when you said that last example was great. If you're still on, I wonder which example that was. Maybe we can chat that out for folks. Jolene is an amazing visual analytics developer, so it's great to get her opinion on things. But anyway, Neil, I didn't want to interrupt you. I'm just kind of live chatting with folks here as you're demoing things.
There's a good question here on achieving executive buy-in and how it can be used to paint the overall picture and driving those key decisions. I think when designing for an executive audience, you want to make sure that you are really honed in on the insights at hand. We talked about things like filter, mark, zoom, and exploring your data. Another thing we talked about was the colors used when there could be too many colors. You really want to have, a few colors. You want to have a few charts that really hone in on the insights that are important to the executives. And to do that, you really need to understand your audience, and you need to take an iterative process of research and conversation to understand what is it that audience is trying to see, and then custom tailor your dashboards that way. It's incredibly important.
Yeah, and I think the 3-level hierarchy of overview first, filter, mark, zoom, and then details on demand, that's perfect for executive consumption, because they want to see the overall broad picture. They want to be able to zoom into where the action is, and they want to see the detail there. So that is a part of our mantra is, it's just general good principles to be able to want to do those 3 levels. But I think it really does play well when you're trying to make a point to an executive. And the executive always wants to come up with a smart idea. They would say, well, what about over here? Let me look at this part of the action. And you want to make sure that's covered as an insight comes out that an executive's interested in. So I think that 3-level mantra, I think, is just a great general set of principles. Overview first, zoom and filter, details on demand. That's if you can set up your analyses to give that level of drill down insight, or drill up, drill sideways, whatever, that I think really satisfies a lot of executive audiences.
Right. So carrying on, I think we have one more map to show, we have a couple more maps to show. So there's a heat map. So this is also very efficient use of the real estate. Here you have fixed cell sizes. So unlike the tree map, where in the tree map you have cell sizes that vary by some variable, some dimension in your data, here you're actually going to have fixed heat sizes. And this allows you to see clusters of data in 2 dimensions. So this is COVID-19 hospital admissions by time of day and by day of month. And you're able to see both a wave starting here towards the end of towards this August 2021. There's a wave of cases that have come in as compared to prior dates in the year. So you have the year on the x-axis and the time of day on the y-axis. We're also seeing that people tend to come in late at night, and also around 3 p.m. middle of the day. That's when people are coming in, but there's a lull 5-6 a.m. in the morning, and that kind of persists throughout the year. So by looking at these fixed cell size, we're seeing those clusters of data very well, and that is for a heat map. Another type of heat map that's shown here is a variable correlation. So how is one variable correlated to another variable? That's shown on the matrix over here on the left. And we have a network chart next to that actually maps those variables to each other by their strengths of correlations. So the network chart is a really cool visualization that this can be non-geographic as well, this network map. And this can map out actual relationships of variables, especially in multivariate space when you have lots of variables, how are those variables related to each other. In this example, we're actually looking at clusters of transactions on opioid data. So opioid transactions between the sellers, which are the center of the clusters, and the buyers, which are the individual points, and how how that network is mapped out. And this was used to start looking for trafficking and illicit trafficking of opioids and with the DEA in these opioid transaction data.
Yeah, and the network there represents who wrote the prescription, where the prescription was filled, who was it filled to, where did it end up. So those sort of relationships where the network chart or network map really is fantastic when you've got that sequence of connection points. Nodes and edges is what the network chart represents. And if you've got relationships like that, it really shows those up well.
Yeah. It's a very, I think, abstract, complex, and sophisticated way to look at data in a spatial way. So I really love the network chart, the network map.
Yeah.
So let's talk about data layers for a second. So we talked about points, lines, and polygons, and you might use this to represent data in different ways on your map in whatever visualization tool you're using. Now in Spotfire, the tool that TIBCO offers, the visual analytics tool, you can have multiple layers that stack on top of each other, and you can represent points on top of lines, on top of polygons, all representing different data tables and different layers. So let's talk about what are these different layers. So the marker layer is the most common type of layer. This is sometimes called a bubble map or a marker map, a point map. And these are individual points to represent your data. So this is very common. The feature layer this is now showing different neighborhoods. What we're looking at here is real estate prices in Victoria, Australia. Each of those points that we were looking at, each of these individual points represents a property. And then when I go into the feature layer, we're starting to see a geometry, a polygon that represents the neighborhoods and the average income per neighborhood. So that's kind of like our Chord Plots map. We can use a feature layer to represent those geometries and polygons. We can also use web layers. So in the background, we have live traffic going. So web layers are non-interactive in terms of clickability, but they can be live and they can just represent your data very quickly and very efficiently. They tend to use a lot less resources than bringing in each of those geometries, because each part of the web layer is rendered as a tile image. And so you have multiple tiles of images that really make up the whole layer. And that's a much more efficient in terms of data transfer and data processing. You might use different background layers. The reason I put background layers in here is that it's important to use a background layer that's appropriate for the data that you're showing. So if you have data that's not very relevant to, let's say, geographical, let's say geological or geographical parts of the Earth, you don't want to have a really rich background layer with all kinds of forests and waterways and all these different colors in the background. You might want to use something that's a little more muted, maybe a grayscale background, something a little more plain that lets your data actually pop out and show a little bit more. If those references in that context is important, let's say you're doing something on ecological study, and you do want to see where the different forests and the different ecological zones are, then you want to have a rich background layer. So it just kind of depends on what type of data you're showing. If you're using something with traffic data, you want to make sure your background layer has roads on it. You don't want to have a background layer without roads on it while you're showing traffic data. And then lastly, there's image layers. So these are ways that you can do here's some other non-geographical maps. You're seeing an injury map on the top right. So how injuries are represented on the human body. Below that, you're seeing a ternary plot. And to the bottom left, you're seeing an airplane seating chart map. So these are images in the backgrounds, and you can represent your data on top of that to create different maps. Do we have any other questions here? No, I don't think we have any other questions. So I'm going to just keep moving, Michael.
Yeah, keep moving, Neil. Yeah.
All right. So spatial operations. There's lots of spatial operations out there. Here's just a few to talk about. We're going to be covering things like the Voronoi polygon, the least cost path, the buffer zone, nearest neighbor, proximity, things like that. So there's different types of geospatial operations, and these are actions that you're going to take on your geospatial data to extract more value out of them. To instead of just looking descriptively at raw data, how can we understand the relationship of that data to each other, to other data in that data set, or to other data in other data sets. So these are geospatial operations. And the first example is actually spatial proximity. We're looking at this New York City demographics again, and this is a proximity to the store. So the store is this yellow star right here. And we want to filter our data down to who's nearest to that store. And then we want to see what income and other attributes there are. So that's why we used a spatial proximity algorithm. We really just used a Habersign formula to calculate the distances from the center of each of the individual census districts here. That's what the geometries are. And the distance of that to the store itself. We can move that store to another location if we want. This video is playing a little slow. So here I'm going to copy some map coordinates, and I'm going to place those map coordinates into a new location here. And I'm going to move the store to another area and find the spatial proximity to that new location. So it's going to totally change the context of the data around it. Now we're looking at a totally different demographics. We're looking at different income. We're looking at different commute times to work, different populations, different unemployment levels. So it's all relative to that proximity analysis. And then buffers are another way that you can get value out of your analysis by understanding what is the area around certain objects. And maybe you don't want to do something within a certain region around that buffer. You want to make sure certain objects are spaced appropriately a distance away from each other. So what this is actually looking at horizontal wells that have been drilled into a reservoir. And you don't want to put the wells too close to each other because they need drainage space. So I can actually move a slider. So I can select some wells, and that's going to show these thin lines. And then I can move my distance cutoff, and that's going to increase the buffer zone. And I can see, okay, how do I actually, what is the available space available given whatever buffer zone I choose? So that's a spatial buffer. And there's also, this is feature extraction. It could be called a geometry or point extraction as well. There might be a better term for this. But with this type of extraction, what we're doing is, as I click on a river, these blue lines are rivers, I might want to do a interpolation of different data along the river. If you're familiar with spatial data, you'll know that that line is a certain record on its own. So the whole line represents one data point. And what I want to do is split that line up into different data points so I can do an interpolation of values along there, or I can find something that's nearest to that line. I can a point that's nearest to that line. There's many reasons why I might want to extract that geometries. So what we're using is an R script that as we click on the data, it does a little calculation and says, here are all the vertices along your line. And when you have a gap of over 100 feet, I'm going to interpolate a new point at every 100 feet. And what that allows us to do is actual spatial join and interpolation. So you can extract those points. What we have here with these red dots are measuring stations along a river network. And I want to know what my pollutants are like along the river. But I only have these points along the river. I don't have the full network. So I can extract the points off the rivers. That's giving me these black dots by doing that extraction. And then I can do a spatial join and say what's nearest to my red dots and give myself a little bit of a join between the two data sets. So I'll play this. And as I move the slider at the top left for the spatial join cutoff, you'll see that it includes next to the red circles, it includes the nearby river network. So now we have a lot more shown there. And as I zoom in, you're seeing these different colors. What that's doing is actually then saying, hey, you have different measurements of pollutants at different areas along the river. Let me interpolate along those points you extracted and give you what the pollutants are like at every individual level along that river. So rather than having just one object that's just a line, a polyline shape, where I couldn't really get this type of granular information, I've then extracted the points, and I've done a spatial join that allows me to interpolate and find the gradient of the pollutants along the river. So these are all types of different types of operations. I think I have one more here. Yeah, so this is my last one on spatial operations is intersection. What we have is different trade areas in green. A trade area is if you start from one point and you want to do a trade area of, let's say, like 2 miles, how far can you travel along the roads or waterways and bridges in 2 miles in any direction? So it won't be a perfect circle because the roads are going to dictate what 2 miles is in any direction you go. So what this is actually showing is the trade area of a couple miles around different cities in the Bay Area. And behind that, you have in blue, you have the census district demographics. So you have things like median age, how much college education, the percent of the population over 18, the percent of the population over 65, and the income of those populations. So when I hit play here, what you're going to see is an intersection of the green polygons against the blue polygons. As I move the sliders, you're seeing the bars change, and that's saying, okay, I'm filtering out right now. I'm filtering out the median age, and I'm filtering to a younger median age. Where are younger people located? And it's going to actually intersect that with the green trade areas and tell me that's where those younger people are located. Here's where this population is located, that population is located, et cetera. But it's an intersection of those two polygons from two different data layers on top of each other. Up next, we have spatial patterns. With spatial patterns, these can be different ways to help just the visual interpretation of the data. One I really like is the grid bin generalization. So looking at insurance claims in Florida, on the left, you're seeing that bubble map, and you're seeing lots of points overlap each other. A very simplified way to do this binning is in a grid shape, which you're seeing on the right. Now, I made that very coarse. I probably should have made that into a more granular bins. But what that does is it allows you to generalize the data that's all overlapping on top of each other and get a sense of where the colors are the types of insurance claims. So where are the most common types of insurance claims per area over there. And so that helps you actually interpret a lot of data that can be overlapping on top of each other. Another way to do it is hex bins. And so similar to a grid bin, this is going to help generalize a lot of points into non-overlapping points, non-overlapping hexagons, and they're arranged in a hexagonal shape. And why a hexagonal shape is better than a grid shape is you can actually fit more hexagons into an area than you can fit into a plane. You see, in terms of a regular tessellation, in terms of a rectangle or a square, you're actually getting 13% more coverage with a hexagon. So the hexagon's more efficient than covering the plane, and this translates to better sampling. You're able to actually understand the data better. You have less of a bias in the interpretation. When you have a grid, your eyes are gonna look up and down, up the verticals and then across the horizontals. And that introduces a bias where you're not really seeing the angles. The hexagonal binning will actually help you see the angles as well and reduces that spatial bias. And next we have density generalization. So when you have a lot of points together, you can actually generalize those to show, here we have a contour map or isopleth map that's showing how many points are together. And we're actually able to generalize across the United States to see the population in the, where's my mouse? Here it is. the population in the Northeast, and you're able to better interpret this data. So generalization, we're talking about generalization. That's really just taking a lot of granular data and generalizing it, using it to make it more interpretable by making it more general. And so that's what these shapes, these isoplets are doing with the density generalization.
Michael? Yeah, and you can build upon the concepts that Neil outlined. You see on the right-hand side, we're starting to do calculations on the map. And so let's go into the next slide. I think we've got some, generalizations of that. And it's really, you can do quite sophisticated calculations on top of the map, and you can join data and from the predictions and all that kind of stuff. So this is an example where we did, actually it was part of a hackathon where you're looking at wind speed patterns in Texas. So those triangles are weather stations. I think there's 72 of them across the state. And then you're trying to predict the wind power generation from wind farms, which are the white circles. So you're able to lay down a contour analysis with a certain smoothing type value that you can either estimate from the data, or you can put a flexible slider onto it. And so that contour map, we're predicting a Z variable within a region, and that Z variable is the wind speed at those weather stations. And the idea is that if you can get, you've got lots of data coming into the weather stations on wind speed from all 360 degrees and everything. If you can start to predict, or firstly start to analyze the isopleths of wind speed across the state, then you could pick off the predicted value from that at the different wind farms and get a prediction of the power generated into the future from those wind farms. So that's what that contour analysis does there. If you go to the next slide, we can show one of the winning entrants in that hackathon, where you can see the contour smoothing slider down the bottom left-hand corner. You can slide that around and change the wiggliness of the contour analysis. And again, you're picking off from those contours on wind speed that you've fitted onto the weather station data. You're now picking off the value from that contour analysis that's closest to the wind farm location. The wind farm locations are being clicked on right now across the top there. There's 20 or so wind farms that we're now predicting, from the spatial data, the power generation. So the bottom right hand is there. The y-axis is the predicted power versus the wind speed. And that's that power predicted from wind speed at each of the turbine locations gives you a pretty interesting forecast about what power you're going to produce as a function of wind speed into the future. So really cool analysis, because you're not just doing a summary of visually on the map of the wind speed. You are doing that, but you're now using that to join into these wind farms and get the predicted power from individual wind farms, and that allows you to manage the energy production and delivery to the grid. So very powerful. The way the principles Neil outlined, you can build upon those to create these, predictive models in a very powerful way.
Yeah, I was just going to say, this is our renewable energy hackathon winner, Jolene, and we have Jolene in the audience today. So Jolene, credit to you for your great work here on this hackathon. Yeah,
it's really exciting, I think, to see these tools that you're using for displaying data to actually, be used in model building and prediction from one data set to another based on in this case, the contour analysis of the wind speed at the weather stations. A really cool example. We've got another hackathon at the Analytics Forum this year on renewable data that we're pretty excited about. So I hope you guys hope you can join us with that. Let's go to the next slide, Neil. I think we got another example here of where we're doing a heat map heat maps and contours are two really good building block tools to get to predictions and summaries on data. So this is COVID-19 data, and we've got county level case counts, and we're going to do a hotspot analysis on top of that. So in this case, we're looking at the trend of hotspots. We're using the centroid of the county data as the Z value, and we're doing a lowest smooth of that Z value, smearing that around the individual counties. And we're coloring by the low S of the Z value estimated at a very fine grid. And you see how that gives you an impression as to where the hotspots are. So yeah, conceptually very simple. Take the centroid of the county, get the Z value for the cases, and low S smooth those Z values, and then color by the low S evaluated at a fine grid. Really nice piece of work here, Neil, on this. I know you kind of really knocked it out on that one. But it's another example of really how you can do a calculation on spatially that really elicits data and insights from data that you might not have been able to get those insights from the raw data. You're kind of bringing that out with that contour analysis and coloring, using that Z value of the centroids. But let's go to the next one, because I think we've got some really interesting calculations here. Like this is called a Voronoi Tessellation. So if you've got a bunch of points on a graph, you can draw a polygon that so that the points inside each polygon, all the points inside that polygon are closest to that dot than they are to any other dot. That's the idea of a tessellation. So that concept can be used to, again, elicit insights from a variety of data sets. So if we go to the first example, here we've got an example where we've got wells and geology samples, and you put down the Voronoi polygons around the wells, and you can see what are the geology samples that are relevant to those well locations. Because and there's the well locations. Is that right? What are the orange points again, Neil?
Yeah, that's right. The orange are the wells, and those tessellations are shown on the geology samples. So when you have a lot of geology samples together, you're going to see more tessellations, more polygons. And then towards the extremities where you have less samples, you're going to see larger polygons. But as you kind of pointed out, every point within a polygon is closest to the centroid of that polygon than it is to any other centroid of any other polygon.
Right. And so this analysis can be used, for example, the porosity, permeability of the geology are good predictors of the amount of oil or gas generated from the well. So you can start to build machine learning models by, again, spatially joining data, in this case through the Voronoi polygon. There's another example here where we've got we're going to locate health clinics on a map based on where the demand is. So we do quite a bit of this in retail as well as in healthcare. In this case, we're going to set up these, in first case, 7 clinics. Where would you put the 7 clinics to meet the needs of the people? And where would you put 16 clinics? And you can see how the orange points here are the clinics, and the blue points here are the people who need to get to the clinics. And you can see how you can efficiently design a number of clinics to meet the needs of the community in each case.
Yeah, and this is a perfect example where the orange diamonds are the centroids of each of those polygons. So each of the individual points on each of the individual blue dots are patients, and we're able to see, hey, these patients are closest to the diamond in their polygon.
Right. Now, this is as the crow flies distance. We also, I think, might have an example coming up where we're doing actual driving distance on roadways, right? Do we have that one coming up soon? Or
let me see.
Go back to the deck and see where that one. Oh, yeah, it's the very next slide. Yeah, so that's the very next slide. So in this case, we put down a blue point there in the middle, and we want to see at a certain driving distance, actual distance along the road, what healthcare facilities are within a certain driving distance. So in this case, Neil, I think we've got a 5-mile driving distance from the blue point gets you, the healthcare facilities that are within that driving distance notated there in the orange squares. So that starting location, the blue diamond, you can see with a drive distance of looks like 4.5 miles. This is in New York. Neil just changed it to Seattle. Okay, so now we're over in Seattle. He's going to put in the coordinate system of the coordinates of a particular location and choose like a 5-mile driving distance. And now we're going to see which healthcare facilities within 5-mile drive distance, in Seattle from the point that he chose on the map. So there you see them. There's looks like about 20 or so healthcare locations that are within 5 miles of that blue point. And notice how it takes into account, driving down different highways, crossing over bridges. This is the other examples we showed were kind of as the crow flies. This one is actual driving distance and a perimeter or radius for that. Awesome. And now I think, some other examples of advanced calculations. If you have a certain set of distribution centers and you want to make deliveries to stores, this is an example where we're going to see which deliveries are made from which distribution centers to which stores. There's a constraint on the maximum number of trips that you might make per distribution center per day. This example is actually for delivering fresh coffee to coffee stores. And you also want to minimize the total delivery driving distance to get the most efficient delivery route. But you can see here there's 6 distribution centers in the 6 colors there in the Bay Area. So you can slide that around. Actually, looks like we're sliding that down to 5 or so. And now we want to make deliveries to each of the coffee stores, and you can see how those. If we can only make 50 deliveries per day, you see that vertical line there at 50 deliveries per day. You can see how the San Jose, San Francisco, and Fremont distribution centers are meeting the need of all the coffee stores in the region, but they can only do 50 trips per day. And so you can see how the routes are adjusting for that constraint, and at the same time minimizing the total drive time or driving of each of the deliveries. So you can do pretty sophisticated calculations on maps, and display the results in a nice way.
Yeah.
So let's go to the application center, Neil. I think application section. I think this is your piece, right? Oh no, it's me again. Okay, I can talk to it, or you can. In this case, this is seismic data from the energy sector, and literally you get hundreds of data variables by bouncing sound waves off the rock, and you get different angles of the different types of information coming back from the different types of sound wave frequencies that you bounce off the rock. Now they're quite correlated, so typically what we do is do a principal component analysis of them and reduce the dimensionality. And you can see the first visual geo analysis is the first principal component, so multivariate data is being plotted there. The second graph on the right is the second principal component. So they're representing multiple seismic variables, but they're showing them spatially. So you can see the X and Y axes here are actual physical location data. And you can see how the first principal component is finding some structure in the rock, and the second one is finding some other structure. So we go to the next slide. I think we reduced it down to 6, principal components. And you can see each of those 6 components organized by the weights into a self-organizing map, and you can navigate around that self-organizing map to show the structure in the geology on the right-hand side, using the principal component number 1 as the color scheme. Go to the next slide. I think we might have an expanded view of that. No, this is going across to more other sorts of route calculations on the geospatial representation. Neil, can you take this one?
Yeah, so this is on our least cost path. So a geoanalytic application of finding what is the fastest path, what is the easiest path from point A to point B. This is using a route analysis that's tied to Google Maps and Google Street View. But what it's doing is actually taking into account the traffic data, the road networks, and it's doing a calculation of the navigation route from one point to another. So least cost path. It finds the corridor of least cost to an endpoint.
Oh, this was me. Okay, so Semi, we're going back and forth pretty quick here, not allowing me to multitask. So let's see. This one is a wafer map. So this is a spatial representation on a high-tech manufacturing wafer production. You can do that on a single value on each location on the wafer map and smooth it like across the top row here. So we call these parametric wafer maps. And then bin maps are when you've got multiple test values at each location on the wafer, and you can also do a analysis or a smooth or a summary of those multiple values at each die. And then finally, the overlay plot, when you've got multiple layers, just go back one, the bottom left graph there. When you've got multiple layers, you want to see how well aligned the different layers are. That's with an overlay plot. So a variety of different graphics that you can do on a semiconductor wafer map representation. Next slide. And you can trellis those as well. So this is a composite bin map where you've got a statistic for a group of wafers, like a lot of wafers, for example. And this is a bin map where you can show those, with a trellis variable showing different setups, where you might want to look at patterns on the bin maps on different lots and on different, condition variables that are part of the manufacturing process. Next slide. And once you get a certain pattern, you might want to classify other wafers to fit that pattern. So this looks like a little kind of circular ring type pattern that's been identified here. And often the yield is related to those patterns, whether you've got a scratch or an edge ring, or it's important to identify those sort of patterns and predict the yield that you might get based on the patterns. Next slide. I think we've got a blow up of that. So this is the process here where we're identifying a pattern visually. And again, the human eye is really great at that. You can quickly find a pattern. And then you can ask the software, go find me other examples of that pattern in the data set that I have. And so you can form up actually a training set to be able to train a model to recognize those patterns, based on that original pattern that was of interest. Now that you have that model, you've trained it up, you can now use that to classify new wafers that are coming in on the event stream, so that you can quickly find this is a checkerboard pattern versus an edge ring pattern. You can quickly understand what sort of patterns you're getting coming off the manufacturing process, and how you might want to either take remedial action or bucket out the results into different groups. So yeah, those are some examples from the semiconductor industry. Now, Neil, I think you're going to take a couple examples and put together the concepts of space and time in some single data sets, right?
Yeah, so we talked about time, we talked about space. Now let's bring it all together with some space-time continuum. So we have just a few analytics applications before we wrap up today. So kind of close out with some examples of space and time combined. This is a flight surveillance application where you're looking at real-time flight streams. This is collecting data from an SDR antenna. It's collecting information on altitude, speed, heading, flight ID, and location, and it's represented in Spotfire as an interactive chart. So we can see a flight as it's actually coming into the Boston airport and getting ready to land in that Boston airport. So here's a more detailed view of that. So this is looking at different flights as they're taking off, coming into the airport. We can click around and select different flights. We can see their flight distance, see as flights are approaching the airport, click on them to hone in on those flights and analyze those flights as their altitude's dropping and see if we're ready for landing. So it's really interesting little fun application that we built just with a $20 SDR receiver, and it's hosted in our Boston TIBCO office. We're able to pick up live radio signals and create this type of application.
Awesome.
Yeah. We also have some hurricane tracking here. Let me see, do I have a video here? So looking at different shapes of hurricane polygons coming in. So these are temporally animated. They're animated over time. We can demonstrate their projected paths. And then on the bottom left, there's a little sample dashboard that is actually predicting insurance claims as insurance claims are coming in. So we can see a hurricane coming in, and by the strength of that hurricane, we can actually predict how much damage that's going to do and how many claims are going to come through. And so that's an example of both the spatial component of the hurricane coming in and the temporal component of making that prediction. And then Michael, if you want to talk about our dynamic pricing app.
Oh yeah, for sure. In this case, we actually fit a model for estimating the probability that a quote is going to get accepted by a certain customer, depending on their attributes. And we produce those quotes, and This is like self-service insurance type applications where you fill in some details and you get a quote for a certain insurance policy. And then you can look at the uptake of those quotes spatially. So in this case, this is an example in the United Kingdom, and you can see on the left-hand side the map there showing the spatial uptake of different quotes. But you can also see across time how those quotes are being uptaked, being accepted or rejected. So this is a great example of you've got a time sequence that's happening in real time, but you're also layering out the predictions and the actual results on a spatial representation. And then just wrapping it up here, I think this is maybe our last example. We do a lot of work with the F1 team at Mercedes, and this is an example where actually someone's sitting in a video game simulator. They're driving around a track, and we're doing a prediction there of their lap time. So we're, data's coming through live on the time sequence. We're predicting on that, but we're also showing spatially on the track where where the person is and what their predicted lap time might be. So there's a lot of great examples like this on space and time combined. It looks like we've got a bit of a drill down here, Neil. So we're looking at the lap time prediction, sector lap time prediction, monitoring that on top of the track. And you can see here how that, the lap time is being predicted as the actual lap is in progress. And there's different variables associated with predicting the lap time. Sometimes we simulate a lot of these before the event and to help set up the car and configure the car. And other times we're just trying to figure out how to overtake the car in front during the race. A lot of exciting stuff goes on in the analysis of F1 data, and we've got we just started the race season here. You can see when you highlight, a prediction, and what happened on the track where that jump occurred. Looks like somebody went off the side of the track a little bit, which impacted, the prediction of lap time, during that event. But yeah, ESPN does a great coverage of F1 and this whole Drive to Survive series on Netflix. Pretty exciting stuff, and lots of great examples in analytics on the event stream and also spatially as the cars go around the track. So I think that's kind of what we had today, Neil. Right? That's the last example. I hope you were able to get some good insights out of that today. We did a recap on the time analytics in time at the beginning. We also did a recap on perception, getting estimation and inference and insights, how to configure your visuals to get the most out of that. That 3-level mantra of overview first, drill and zoom to the area of interest, and get details on demand is a real good process for communicating insights from visual analytics. And then we spent a lot of the time today on the spatial aspects and the space-time combinations. I think that's it, Neil. We've got a few links there for folks to go look at some of the things that we showed today on the demo gallery. And I hope we can see a lot of you at our analytics forum this year, and especially in the hackathon that we're excited about.
Yeah, we have our TIBCO Analytics Forum. It's free to join. There's a renewable energy hackathon again. We're going to have lots more material on how to improve your own skills in visual analytics. We have Nadia Bremer is a speaker. So if you're familiar with Nadia Bremer, she has a great, let me see if we can pull her up.
Nadia is a visual analytics expert, guru, JavaScript developer, has created a bunch of visual analytics for data viz as well as for art, and a very active, user. Neil's trying to show something now, but maybe it doesn't show up. Visualcinnamon.com is her website. Oh, there we go. And you can see some of her work there. With our Spotfire mods being JavaScript based, we thought we'd get a JavaScript thought leader in to show you all the extent of what you can do in that environment. So yeah, we're excited for the Analytics Forum, and feel free to reach out to us. It's June 13th to 15th, the Analytics Forum, and feel free to reach out to us in the meantime.
Yeah, it's analyticsforum.tibco.com. That's how you can find it. Analyticsforum.tibco.com. Well, thank you all for joining today, and we had a lot of fun. Hope you did as well. We actually made it to the end of our presentation today, Michael, so that's good. We have a lot of content, so
Yeah.
Covered a wide breadth of material, and yeah, thank you all for joining. We'll catch you next time.
All the best, everybody. Have a great day.